Imagine driving an old car at highway speeds through a building zone filled with hidden obstacles. That's basically what 3IATLAS is doing right now in the space belt.
Except the car is 4 billion years old.
The highway stretches across millions of kilometers, and a crash would destroy the only samples of alien chemistry we've ever found. This space visitor is writing its survival story in real time. Each day brings it deeper into the cosmic shooting gallery that lies between Mars and Jupiter. But here's what makes this meeting truly special. We're watching it happen. Stay until the end as we look at whether this ancient giant can survive the most dangerous crossing in our solar area, and what happens if it doesn't. By the way, if you enjoy drifting off to these cosmic stories, feel free to subscribe or simply share your thoughts down in the comments. It helps others find their way here too. But for now, let this space journey carry you. And if you're ready, let's begin. Part 1, The Visitor from Beyond. On July 1st, 2025, in the dry mountains of Chile's Atacama Desert, a robot named Atlas was looking for danger, the space rock. Early warning system had been watching the southern skies for years, listing every rock that might one day threaten our world. But what it found that night was something else entirely. A faint dot of light, barely visible against the star background of Sagittarius, moving with purpose through the darkness. Within 24 hours, NASA's smartest minds had run the math. The numbers told a story that made star watchers around the world stop what they were doing and stare at their screens. This wasn't just another chunk of space junk.
This was a messenger from the stars.
They named it 3IATLAS with the formal catalog name C2025N1, the 3I marking it as only the third confirmed space visitor we've ever found. Think about that for a moment. In all of human history, we've watched billions of comets and rocks circle our sun, but only 3 times have we caught something that doesn't belong to our solar family. What makes an object from space isn't just distance, it's math. When our computers traced Atlas's path backward through space and time, they found an orbit so extreme it challenged our solar system's gravity design. Its stretch measured around 6.1. To put that in view, Earth's orbit has a stretch of 0.017, nearly a perfect circle. Even the most stretched comets from our own cloud rarely go beyond a stretch of 1, but Atlas was moving on what scientists call a strongly curved path, coming toward our sun at speeds that could only mean one thing. It had traveled here from space between stars. The speed readings were amazing. Atlas was racing toward our sun at about 60 kilometers s. That's over 200,000 kilometers h. No gravity boost from Jupiter or Saturn could speed up a local object to such speeds. This visitor had been falling toward us across the galaxy for millions, perhaps billions of years. Its starting point made the discovery even more interesting. When star watchers traced its path backward, they found it arriving from the direction of Sagittarius toward the central areas of our Milky Way galaxy. Not from the thin outer reaches where our sun lives, but from the crowded ancient star neighborhoods closer to the galaxy center. What stories might such a traveler carry? The safety question came up right away, as it always does when the public hears about incoming space objects. But Atlas posed no threat to Earth. Its closest visit would happen in December 2025 at a comfortable distance of 1.8 space units, about 270 million kilometers away. That's farther than Mars ever gets from Earth. We would be safe watchers to whatever happened. But the Sun was a different matter entirely. Atlas was on a crash course with our star's influence scheduled to reach its closest point called perihelion around October 29th to 30th, 2025. At that moment, it would be just 1.36 to 1.4 space units from the Sun's surface, well inside Mars's orbital path. For a space visitor that had spent forever in the frozen darkness between stars, this meeting would be life-changing. Already, telescopes were finding the early signs of awakening. As Atlas drew closer to our Sun, the ancient ice locked within its center began responding to star radiation. A faint cloud of gas and dust was forming around the central body. The beginnings of a tale were becoming visible like a ghost appearing in the cosmic void. The Gemini South Telescope captured detailed color pictures on August 27, 2025, showing the subtle colors of melting materials. These weren't the familiar signs of solar system comets. Something different was happening here, something that spoke to alien chemistry and formation conditions unlike anything in our local area. Guessing the size of Atlas proved hard. Early observations suggested a center anywhere from a few kilometers to 10 or 11 kilometers across, larger than our first space visitor, the cigar-shaped Oumuamua, but still small enough to fit easily within a city on Earth. Yet size can be tricky when dealing with objects whose surfaces and makeup remain mysterious. What we were seeing was never seen before, a space comet awakening in real time as it met our sun's influence. For the first time in human history, we could watch materials from other worlds, substances formed around alien stars, react to our local star environment. Every observation was a glimpse into chemistry and physics that had grown in cosmic conditions completely foreign to our experience. This story exists because Atlas represents a once-in-a-lifetime chance. Unlike the quick flybys of previous space visitors, this object was scheduled for a lengthy show, spending months within range of our most powerful telescopes and spacecraft. We could study its makeup, watch its activity, and record its interaction with our solar environment in never-before-seen detail. But there was something else about Atlas that made it special, something that would soon capture imaginations and create controversy around the world. Its path wasn't just from space between stars. It was perfectly lined up to thread through one of the most dangerous areas of our solar system. As Atlas raced toward its solar meeting, it would have to survive a challenge that has destroyed countless smaller objects throughout cosmic history. The space rock belt was waiting, and for the first time, we had a front row seat to watch a space visitor attempt the crossing. Part 2. Origins and Guesses. Where does a traveler from the stars call home? For Atlas, the answer lies written in the math of its motion, in the subtle clues hidden within its path across our galaxy. When scientists traced its route backward through space and time, they found something remarkable. This wasn't just any random wanderer from the cosmic wilderness. The path calculations pointed toward membership in what star watchers call the Milky Way's thick disk, an ancient star population that formed when our galaxy was young and wild. If this analysis holds true, Atlas could be very old, possibly several billion years older than our entire solar system. Imagine while our sun was still a swirling cloud of gas and dust. Atlas may have already been wandering the galaxy as a frozen piece of cosmic history. The thick disk represents our galaxy's middle age, a time when star formation was messy and metal-poor stars ruled the cosmic landscape. These are the star neighborhoods where planetary systems, if they formed at all, would have been very different from our own. Lower metal content, different chemical amounts, alien formation conditions that could produce comets unlike anything in our local experience. But how does a comet become a space traveler in the first place? The process is both violent and common throughout the galaxy. Every forming planetary system is a battlefield of gravity chaos. Giant planets move inward and outward, their massive gravity fields throwing smaller objects into the void. Star meetings between neighboring stars can gravity strip entire comet populations from their parent systems. Close passes by massive objects can launch icy bodies on curved paths that carry them into space between stars. Current models suggest that for every comet that remains tied to its parent star, dozens or hundreds are thrown into the galaxy wilderness. Multiply this by the billions of planetary systems in our galaxy, and you begin to appreciate the scale of space traffic flowing through cosmic space. Atlas isn't unique. It's one example of a vast population of wandering worlds. Early attempts to measure Atlas's physical features revealed interesting limits. Light observations suggested an upper size limit near 10 to 20 kilometers, making it much larger than our first space visitor, Oumuamua. which measured only a few hundred meters in its longest part. Size matters in the comet business. Larger objects keep their melting materials longer and can survive more extreme solar meetings. But it was the chemical analysis that truly set ATLAS apart from anything we'd seen before. When the James Webb Space Telescope turned its heat-sensing eyes toward the growing cloud, it found something amazing: an unusually carbon dioxide-rich environment. The ratio of carbon dioxide to water vapor measured about 8.1, among the highest ratios ever seen in any comet. This chemical signature tells a story of formation conditions unlike those in our solar neighborhood. Carbon dioxide becomes the main ice only under very specific situations. Either formation near the carbon dioxide ice line in a planet-forming disk, or long exposure to galaxy cosmic radiation that can transform water ice into other compounds over millions of years. Both scenarios point to an origin story basically different from local comets. Some researchers have guessed about ejection from a low-metal red dwarf system versus a sun-like star. Red dwarfs rule the thick disk population and have different planetary formation chemistry. Their livable zones are closer to the star. Their planet-forming disks may have different temperature and pressure gradients, and their lower ultraviolet output could preserve certain ice makeups over long periods. Testing such guesses will require detailed light analysis as ATLAS approaches the Sun. The light studies added another layer of mystery. Early observations showed unusual light behavior compared to typical solar system comets, suggesting differences in grain size, texture, or makeup within the cloud. These are the kinds of subtle clues that can reveal the internal structure and formation history of an object that has spent forever in the space between stars. Comparing ATLAS to our previous space visitors highlights its uniqueness. 2I Borisov, discovered in 2019, appeared remarkably similar to solar system comets in its makeup and behavior, a familiar visitor from an alien system. Oumuamua, on the other hand, showed no clear comet activity and had a mysterious speed-up that continues to create scientific debate. Some recent guesses even suggest it could have been a fragment from a Pluto-sized object broken apart by star meetings. ATLAS seems to occupy middle ground, clearly comet-like in its growing activity, but chemically different in ways that reveal its foreign origin. This combination makes it scientifically precious, familiar enough to understand, alien enough to teach us something new about planetary formation throughout the galaxy. What we still don't know could fill libraries. The exact center size and shape remain uncertain, awaiting higher quality observations as the comet brightens. Its spin period and axis direction are mysteries that will influence how evenly or unevenly it sheds material. The detailed chemistry beyond carbon dioxide and water awaits more sensitive light analysis. Most importantly, we don't know how its activity will change as solar heating gets stronger. The next few months would bring never-before-seen observational chances. The Hubble Space Telescope was already planning regular watching sessions. Ground-based 8 to 10 meter telescopes were coordinating campaigns to track makeup changes. Multiple spacecraft throughout the inner solar system were positioning themselves to observe from different viewpoints. Each observation would be a first, the first detailed study of space chemistry reacting to our Sun, the first real-time watching of alien materials under solar radiation, the first chance to compare directly the products of star formation in different galaxy environments. ATLAS wasn't just a comet. It was a time capsule from the ancient galaxy, carrying samples of chemistry and physics from cosmic conditions we can barely imagine. But before we could decode all these secrets, ATLAS would have to survive its journey through our solar system's most dangerous neighborhood. The space rock belt was waiting, populated with millions of objects that had been quietly orbiting the Sun for 4.5 billion years. For a space visitor racing through on a curved path, that region represented a cosmic shooting gallery, unlike anything it had met in its forever of wandering. The question wasn't just scientific curiosity anymore. It was survival, Part 3, the space rock belt, a dangerous crossing. Between Mars and Jupiter, lies a region that science fiction has painted as a cosmic minefield. Millions of rocky pieces tumbling through space in messy orbits, waiting to crush any spacecraft foolish enough to venture into their domain. Hollywood loves the drama, heroes dodging space rocks at every turn, their ships barely escaping crash after crash through the cosmic debris field. The reality, as is often the case with space, is both more ordinary and more fascinating than fiction suggests. The space rock belt is indeed populated with millions of objects ranging from dwarf, planet-sized, Ceres down to countless smaller pieces and dust particles. But space, even in the most crowded regions of our solar system, remains hugely empty. Imagine Earth's orbit as a highway. The space rock belt would be like a section of that highway where instead of one car every few meters, you might meet one car every several thousand kilometers. The average separation between big space rocks is measured in millions of kilometers, distances that dwarf the size of the objects themselves. NASA's numerous missions through the belt have all crossed without incident, proof of the vastness of space, even in its most populated regions. But ATLAS isn't taking the usual route. Most space rocks orbit the Sun in roughly the same direction as the planets, what star watchers call forward motion. ATLAS, however, is traveling on a backward path, tilted at about 175 degrees to the flat plane. This means it's moving basically backward relative to the belt's native population, creating relative speeds that are much higher than typical. Think of it as driving against traffic on a cosmic highway. While the risk of crash remains very small due to the vast distances involved, any meeting that does occur will be far more energetic than the gentle bumps between objects moving in similar directions. When objects crash at speeds of tens of kilometers per second, the results are spectacular and usually destructive. The belt itself is far from uniform. The thickest concentrations lie near the flat plane, the same geometric plane that contains Earth's orbit and most other planetary paths. ATLAS's path, despite its extreme tilt, passes very close to this plane, meaning it will slice directly through the belt's most populated layer rather than safely passing above or below it. The space rock belt's residents are a diverse population. The largest objects, Ceres, Vesta, Pallas, and Hygeia, are massive enough to have kept round shapes and complex geological histories. Below them, thousands of irregular pieces represent the shattered remains of larger bodies, proof of billions of years of crash evolution. Many of these objects show makeup diversity that speaks to different formation conditions throughout the early solar system. There are the carbon-rich C-type space rocks, dark and primitive, preserving materials from the solar cloud's outer regions. The metallic S-types, likely pieces of separated bodies that once had molten cores. The rare M-types, almost pure metal, possibly the exposed cores of shattered planet-like objects. Some objects, dubbed immigrants by star watchers, clearly started in the outer solar system before being scattered inward by planetary movement events. For ATLAS racing through this cosmic museum at curved speeds, each object type represents a different flavor of potential interaction. But it's not the large-named space rocks that pose the greatest threat. It's the countless smaller pieces that occupy the size range from pebbles to boulders, too small to track individually, but numerous enough to create a genuinely dangerous environment. The dust part deserves special attention. Micrometer to millimeter scale particles are abundant throughout the belt, continuously created by crashes between larger objects and gradually spiraling inward toward the Sun due to radiation pressure. For a comet like ATLAS developing an active cloud and tail, this dust represents a sandblasting environment that could strip away material and change the comet's appearance over time. Even more interestingly, the dust interacts with the solar wind to create complex plasma effects. Charged grains feel electromagnetic forces in addition to gravity and radiation pressure, leading to instabilities and wave phenomena that could spread throughout ATLAS's growing cloud. The physics becomes a three-body problem involving gravity, electromagnetism,
And radiation, the kind of system that produces chaotic and unpredictable behavior. Yet despite all these dangers,
the overwhelming likelihood remains that Atlas will cross the belt without any significant meetings. NASA's assessment of crash probabilities consistently shows odds so small they're effectively negligible for any reasonably sized object. The belt is more like an ocean with rare islands than a crowded parking lot. Still, negligible isn't zero. And for an object carrying the scientific hopes of an entire star-watching community, even tiny risks deserve consideration. Micro-impacts could trigger localized outbursts, creating temporary changes in brightness or cloud structure. Meetings with dust concentrations could create streaming effects in the tail, temporarily changing its appearance and providing information about the solar wind environment. Perhaps most importantly, the crossing itself represents a unique observational opportunity. Wide-field surveys can monitor Atlas continuously as it passes through different regions of the belt, watching for any changes in behavior that might indicate interactions with the local environment. Solar observing spacecraft can correlate tail disruptions with solar wind conditions, helping to distinguish between local interactions and space weather effects. The question facing star watchers wasn't really whether Atlas would survive. The odds strongly favored survival. The more interesting question was what we might learn from watching a space object navigate our local debris field. Would we detect subtle changes in its activity as it met different dust environments? Could we use its passage to map previously unknown concentrations of small particles? Most interestingly, how would Atlas's alien chemistry and structure respond to the unique conditions within the space rock belt? This wasn't just about crash avoidance anymore. It was about using our own solar system as a laboratory to study materials from another star environment. As Atlas continued its approach, star watchers worldwide were preparing instruments and scheduling observations. The space rock belt awaited, neither as dangerous as Hollywood imagined, nor as safe as statistics suggested, but as something more interesting than either extreme, a testing ground where an ancient wanderer would face its first real challenge since entering our solar system. The crossing had begun, and for the first time in human history, we were watching. Part 4. A tail forms, a warning sign. The change began subtly, almost unnoticeably, as Atlas drew closer to our sun. At first, the space visitor appeared as nothing more than a point of light, no different from countless background stars, except for its slow drift against the star sphere. But as solar radiation got stronger with each passing day, something remarkable began to happen. Deep within Atlas's ancient center, ice that had remained frozen for forever started responding to star warmth. The process is deceptively simple in concept. Sunlight heats the surface. Solid materials turn directly from ice to gas, and escaping vapors carry dust particles along to form a temporary atmosphere around the center. This atmosphere, called a cloud, can grow to sizes larger than planets, transforming a small, dirty snowball into one of the most spectacular sights in our solar system. But Atlas was revealing chemistry unlike anything star watchers had seen before. The James Webb Space Telescope's heat observations showed that carbon dioxide ruled the early outgassing, creating a cloud makeup radically different from typical comets at similar solar distances. Most local comets begin their activity with water vapor as the primary part, with carbon dioxide becoming important only at much greater distances from the
sun. The unusual chemistry wasn't just
academically interesting, it was potentially diagnostic. Carbon dioxide turns from solid to gas at lower temperatures than water ice, meaning Atlas was becoming active while still relatively far from the sun. This early activity could indicate either a surface makeup ruled by volatile ice or internal heating from some other source. Neither possibility matched the behavior patterns of solar system comets. As the cloud expanded, solar radiation began shaping it into more complex structures. Light particles carry momentum, and when they scatter off dust particles, they give a gentle but persistent push away from the sun. At the same time, The solar wind, a stream of charged particles,
flowing outward from our star, turns
some of the gas molecules into ions and sweeps them away through magnetic field interactions. These two processes create the characteristic dual-tail structure
that makes comets so visually stunning.
The dust tail, made of solid particles reflecting sunlight, curves gracefully away from the sun along the comet's orbital path. The plasma tail, made of turned into ions gases, points directly away from the sun regardless of the comet's motion, creating streamers that can extend for millions of kilometers through space. For Atlas, the growing tail represented both beauty and weakness. Each particle lost to the solar wind or radiation pressure was material that had survived the space journey, only to be stripped away during its brief
meeting with our sun. The tail was simultaneously a triumph, proof
that ancient space ice was responding to our local star and a countdown timer, marking the gradual wearing away of irreplaceable scientific samples. The plasma part of the tail introduced additional complications. When solar wind particles meet comet ions, they transfer energy and momentum through electromagnetic interactions. This mass loading can bend the solar wind flow, creating magnetic field improvements and wave structures that spread both upstream and downstream from the comet. The effect transforms the comet into a kind of cosmic weather station, its plasma tail responding sensitively to variations in solar wind density, speed, and magnetic field strength. During periods of intense solar activity, coronal mass ejections or high-speed stream interactions, the plasma tail can be dramatically kinked, disconnected, or even temporarily destroyed, only to reform as conditions stabilize. Atlas's unusual chemistry made these interactions particularly intriguing. Carbon dioxide ions behave differently from water vapor ions in plasma environments, potentially creating new types of instabilities or wave phenomena that hadn't been observed in previous comets. The growing tail wasn't just a pretty sight, it was a laboratory for studying plasma physics under conditions impossible to recreate on
Earth. But there was something troubling about the tail's
development that made some star watchers nervous. The uneven nature of the early outgassing suggested that activity wasn't evenly distributed across the center surface. This could indicate exposed volatile patches, structural weaknesses, or internal makeup variations that might become important as solar heating got stronger. Uneven outgassing creates forces that can alter a comet's rotation, potentially leading to tumbling motions or even structural failure. In extreme cases, comets can break apart completely under the stress of their own activity. The growing brightness and expanding cloud were beautiful to observe, but they also represented increasing stress on a center that had already survived forever of cosmic ray bombardment and thermal cycling during its space journey. The observational data was painting a picture of an object under increasing strain. Brightness curves showed irregular variations that suggested separate outburst events, rather than smooth, continuous activity. High-resolution imaging revealed jet-like features in the cloud, indicating localized sources of gas and dust emission. The overall shape was becoming more complex and dynamic as Atlas approached its solar meeting. Each of these signs individually might be considered normal comet behavior, but collectively they suggested an object that was responding more dramatically to solar heating than typical comets at similar distances. Whether this represented the natural behavior of space materials or a warning sign of impending structural problems remained unclear. The timing couldn't have been worse. Atlas was still approaching the space rock belt, the most dangerous phase of its journey through our solar system. A comet showing signs of instability or irregular activity would be particularly vulnerable to the additional stresses of navigating through the belt's dust environment and gravitational disturbances from larger space rocks. Yet the growing activity also represented never-before-seen scientific opportunity. Every light line, every brightness variation, every shape change in the cloud and tail was providing new information about space materials and their interaction with our local star environment. The warning signs that worried some star watchers were the very phenomena that made ATLAS scientifically priceless. As telescopes around the world tracked the developing tail, a more basic question began emerging. Was ATLAS behaving like a typical comet from an alien system, or was there something more unusual about this particular visitor? The chemical signatures were already proving alien. The activity patterns were showing unexpected characteristics. And ahead lay the most dangerous part of its journey. The space rock belt was no longer just a navigational danger. It was becoming a test that might determine whether this ancient wanderer would survive long enough to reveal all its secrets. The tale that marked Atlas's awakening also marked the beginning of its greatest weakness. Something was stirring in the cosmic depths, and we were about to find out what a space visitor was really made of. Part 5, Historical Parallels, Other Visitors. ATLAS wasn't the first messenger from beyond our solar system to grace our telescopes, and the stories of its predecessors offer both hope and caution for what might unfold in the months ahead. Each space visitor has carried its own mysteries, its own surprises, and its own lessons about the diversity of objects wandering through our galaxy neighborhood. The first confirmed space object, designated 1 burst into public consciousness in October 2017 when the Pan-STARRS telescope detected it racing through the inner solar system. Hawaiian star watchers gave it a name, meaning messenger from afar arriving first, prophetic words that captured both its significance and its mystery. Oumuamua defied every expectation. Its extreme stretched shape, roughly 10 times longer than it was wide, suggested either a highly unusual natural formation or, as some guessed, something artificial. More puzzling still was its lack of any detectable cloud or tail, despite passing well within Earth's orbit. This wasn't behaving like any comet star watchers had ever observed. Then came the speed-up mystery. As telescopes tracked Oumuamua's departure, they detected a small but persistent non-gravitational acceleration that couldn't be explained by solar radiation pressure alone. The object was speeding up in ways that suggested outgassing, yet no gas or dust emissions were visible. The mystery deepened when researchers calculated that the acceleration was roughly consistent with water vapor turning to gas, but at levels too low to detect with existing instruments. Recent guesses have attempted to resolve Oumuamua's contradictions. One intriguing proposal suggests it might be a fragment from a Pluto-sized object that was broken apart by a star encounter, explaining both its unusual shape and its apparently non-icy makeup. Another theory invokes hydrogen ice formed during the object's long journey through space between stars, which could turn to gas invisibly while still providing the observed acceleration. The second confirmed space visitor, 3I Borisov, discovered in August 2019 by amateur star watcher Gennady Borisov,
presented a completely different personality.
This object looked and behaved exactly like star watchers expected a space comet should: a healthy cloud, a developing tail, and light signatures that closely matched solar system comets. Borisov was in many ways reassuringly normal, a familiar type of object from an alien star system. Detailed observations of Borisov revealed water vapor, carbon monoxide, and various hydrocarbons in ratios similar to comets from our own Oort cloud. Its center appeared intact throughout its solar meeting, and its activity patterns followed predictable curves based on solar heating models. If Oumuamua was the strange cousin, Borisov was the well-behaved family member who confirmed that other star systems produce objects basically similar to our own. But ATLAS seems to occupy middle ground between these extremes, sharing characteristics with each while displaying unique properties of its own. Like Borisov, it's clearly comet-like, developing the expected cloud and tail as it approaches the Sun. Like Oumuamua, it's revealing chemical and physical properties that challenge our understanding of typical comet behavior. The path comparisons are particularly striking. Oumuamua entered our solar system at a steep angle to the flat plane and departed without coming close to any major gravitational sources. Borisov followed a more moderate path that brought it relatively close to the Sun but avoided the most densely populated regions of our system. Atlas, with its near-flat backward path, is taking the most dramatic route of all, threading directly through the space rock belt on its way to solar meeting. For additional perspective, consider the recent spectacular performance of comet C 2023A3 Tsuchinshan-Atlas, which captivated observers throughout 2024. This solar system comet provided a masterclass in comet behavior, developing magnificent tails and surviving close solar passage intact. Its interactions with coronal mass ejections were documented in detail by the SOHO spacecraft, showing how solar activity can dramatically restructure comet tails through magnetic reconnection events. These observations are relevant because they demonstrate that comets regularly experience tail disconnections and reformations without suffering permanent damage. The Solar and Space Observatory has documented hundreds of such events, showing that dramatic tail disruptions are part of normal comet physics rather than signs of impending destruction. This precedent suggests that Atlas might survive even spectacular interactions with solar wind disturbances. However, there's an important distinction to emphasize. While comets often trigger dramatic tail effects when they encounter solar wind structures, there's no credible evidence that comets themselves trigger major solar events. The connection between comet passages and solar activity remains a subject of guessing rather than established science, despite persistent claims in some circles. What makes Atlas scientifically more valuable than previous space visitors is its chemistry. While Borisov resembled local comets and Oumuamua showed no clear makeup signatures, Atlas is providing detailed light data that reveals genuinely alien material properties. The carbon dioxide-dominated cloud represents chemistry that doesn't exist among well-studied solar system comets, offering insights into formation conditions around different types of stars. The observational advantages are also never before seen. Oumuamua was discovered when it was already departing, leaving only a few months for detailed study. Borisov provided a longer observational window but remained relatively faint throughout its passage. Atlas is being tracked from great distances with multiple years of potential observations, allowing star watchers to document its evolution through various phases of solar interaction. Coordination among observatories has also improved dramatically since the previous space visits. NASA, ESA, NOAA and numerous international facilities are sharing data in near real time, ensuring that critical observations aren't missed due to weather, technical problems, or scheduling conflicts at individual sites. Amateur star watchers are also contributing, providing continuous monitoring that professional telescopes can't match. The data processing and analysis capabilities have similarly advanced. Machine learning algorithms can now identify subtle changes in comet shape that might have been missed in earlier observations. Improved light techniques can detect trace species at much lower concentrations than previously possible. Computer models can simulate complex plasma interactions and dust dynamics with never-before-seen detail. Yet for all these advantages, Atlas faces challenges that its predecessors avoided. Neither Oumuamua nor Borisov had to navigate through the space rock belt's dust environment while developing active clouds and tails. Neither encountered the complex gravitational and electromagnetic interactions that await Atlas as it threads through the solar system's most crowded region. The historical precedents offer both encouragement and caution. They demonstrate that space objects can survive solar system passage intact, but they also show that each visitor brings its own unique properties and behaviors. Atlas may follow patterns established by its predecessors, or it may surprise us with entirely new phenomena as we prepare to witness Atlas's passage through the space rock belt. The experiences with previous space visitors provided context, but no guarantees. Each cosmic messenger writes its own story across our skies, and Atlas was about to begin the most dangerous chapter of its billion-year journey. The belt awaited, and with it, the answers to questions that had been traveling toward us since before our species existed. Part 6. Trajectory. Cutting through the meat of the belt. Understanding Atlas's path through our solar system requires thinking in 3 dimensions, with orbital mechanics that would challenge even experienced spacecraft navigators. Most objects in our cosmic neighborhood travel in roughly the same direction as the planets, a stately procession that preserves the angular momentum from our solar system's formation. But Atlas is different. It's traveling backward. The technical term is retrograde motion, and Atlas's orbital inclination of approximately
175 there means it's moving almost
exactly opposite to the normal traffic flow. Imagine every car on a highway traveling east while one vehicle races westbound in the passing lane. That's essentially what Atlas is doing on a cosmic scale, creating relative velocities far higher than anything typical for our solar neighborhood. This backward trajectory isn't just unusual, it's potentially dangerous. When objects collide in space, the kinetic energy involved depends on the square of their relative velocity. A head-on collision between objects moving in opposite directions releases far more energy than a gentle rear-end encounter between objects traveling the same way. For Atlas, threading through the space rock belt against the traffic flow means that any collision, however unlikely, would be catastrophically energetic. The geometry of its approach is equally dramatic. Atlas entered the observable region of our solar system from the direction of Sagittarius, initially appearing as a faint magnitude 16 to 18 object barely detectable by professional telescopes. As it races inward from approximately 3 to 5 astronomical units in July, it will cross the space rock belt's main zone and reach its closest solar approach of 1.357 astronomical units by late October 2025. For observers trying to track this cosmic visitor, the sky path presents its own challenges. During July and August, Atlas remained in the constellation regions of Sagittarius and Ophiuchus, faint enough to require large telescopes and careful tracking to follow its motion. As it brightens with increasing activity, smaller telescopes will eventually be able to observe it. But the rapidly changing position makes continuous observation challenging. The trajectory brings Atlas tantalizingly close to several planets, though close in astronomical terms still means millions of kilometers. On October 3, 2025, it will pass approximately 19 astronomical units from Mars, roughly 28 million kilometers. While this isn't anywhere near collision distance, it's close enough that some Mars-orbiting spacecraft might be able to observe the comet from a unique viewpoint. Later encounters include a passage 65 astronomical units from Venus on November 3rd, and a more distant 0.36 astronomical units from Jupiter on March 16, 2026. These planetary encounters won't significantly alter Atlas's trajectory. Its hyperbolic orbit carries too much energy for gravitational capture, but they provide excellent opportunities for triangulation and parallax measurements from multiple spacecraft locations. The Earth clearance remains safely large throughout the encounter. The closest approach occurs in December 2025 at approximately 1.8 astronomical units, about 270 million kilometers. This is farther than Mars ever gets from Earth, eliminating any possibility of direct threat to our planet. Even if Atlas were to fragment completely, the debris would follow the same hyperbolic trajectory and miss Earth entirely. The speed numbers are staggering in their own right. Atlas's hyperbolic excess velocity, the speed it would have in space, between stars far from any gravitational influence, measures approximately 58 km/s. In some analyses, as it falls toward the Sun, gravitational acceleration increases this to even higher values, creating relative velocities with space rock belt objects that can exceed 100 km/s. To put this in perspective, the fastest human-made objects like the Parker Solar Probe at its closest solar approach reach speeds around 190 km/s. Atlas is traveling at a significant fraction of the highest speeds we can achieve with our most advanced propulsion technology, but it's been maintaining this pace for millions or billions of years. The near-ecliptic backward path creates maximum interaction with the solar wind structures that are most common in the ecliptic plane. This isn't coincidental. The ecliptic plane contains not just the highest density of solid objects, but also the most complex electromagnetic environment. Coronal mass ejections, co-rotating interaction regions, and other solar wind features tend to be most pronounced near the solar equatorial plane, which approximately aligns with the ecliptic. For space physics researchers, ATLAS's trajectory provides an unprecedented opportunity to study how an active comet interacts with various solar wind structures as it crosses different space regions. Multiple spacecraft positioned throughout the inner solar system can observe the same comet from different angles simultaneously, providing stereo observations that reveal three-dimensional structure in ways impossible from Earth-based telescopes alone. The trajectory also maximizes the observational window for ground-based telescopes. Unlike previous space visitors that approached from high inclinations and provided only brief viewing opportunities, ATLAS remains visible from Earth for many months. This extended timeline allows for seasonal observations from different hemispheres, weather backup at multiple observatories, and the luxury of repeated measurements to confirm unusual findings. What makes this path particularly scientifically valuable is that ATLAS will sample multiple distinct environments during its solar system passage. The outer space rock belt region where it spent July and August represents a relatively pristine environment with minimal solar wind interaction. The main belt zone, which it entered in September, provides intermediate conditions with moderate solar heating and complex dust interactions. The inner system, where it will spend October and November, offers maximum solar wind coupling and intense radiation environments. Each of these regions will test different aspects of ATLAS's structure and composition. The outer belt transit revealed its baseline activity level and chemical signatures. The main belt passage will show how it responds to dust interactions and gravitational disturbances from larger space rocks. The inner system encounter will demonstrate whether its center can withstand extreme solar heating while maintaining structural integrity. The backward nature of the orbit creates one additional advantage for observers. The relative motion against the stellar background is maximized, making it easier to distinguish the comet from background stars and to measure its position precisely. This helps with both tracking accuracy and contamination rejection in light-based observations. As ATLAS races toward its October perihelion, every day brings it deeper into the space rock belt's most populated regions. The trajectory that makes it scientifically valuable also makes it vulnerable to the kinds of interactions that have destroyed smaller objects throughout solar system history. The path through the belt isn't just a route, it's a gauntlet that will test everything about this ancient wanderer's ability to survive in our cosmic neighborhood. The mathematics of orbital mechanics had delivered us a perfect natural experiment, a space object following a trajectory designed to maximize both scientific opportunity and dramatic tension. ATLAS was threading the needle through our solar system's most dangerous region, and we had front-row seats to watch what happened next. Part 7: Collision Scenarios. The space rock belt contains some of the most famous names in our solar system: Ceres, Vesta, Pallas, Hygeia. Massive worlds in their own right that dwarf most of the objects humans have visited. Ceres alone measures nearly 1,000 kilometers across, large enough to have achieved water balance and earn classification as a dwarf planet. Vesta, with its distinctive shape and ancient impact basins, represents the battered remnant of what was once a much larger world. These are the titans of the belt, the gravitational anchors around which smaller debris has organized itself over billions of years. For ATLAS, racing through this region at hyperbolic speeds, even these massive objects pose essentially no direct threat. Space is unimaginably large compared to the size of the objects within it, and the probability calculations are reassuring in their astronomical improbability. To visualize the scale, if Earth were a marble sitting in New York City, the nearest space rock belt object might be another marble located somewhere in Los Angeles. The intervening space is simply empty. NASA's assessment of collision probabilities consistently shows odds so remote they barely deserve consideration. Every spacecraft that has crossed the space rock belt from Pioneer 10 in 1973 to the most recent Mars missions has done so without encountering anything larger than microscopic dust particles. The belt's reputation as a cosmic shooting gallery is more Hollywood fiction than physical reality. But Atlas isn't following the same predictable paths as human spacecraft. Its backward trajectory means it's essentially driving against traffic on the cosmic interstate, creating relative velocities that can exceed 100 km/s during chance encounters. While the probability of collision remains infinitely small, the energy involved in any such encounter would be catastrophic. Consider what happens when objects collide at these velocities. The kinetic energy scales with the square of the relative speed, meaning that a backward collision releases roughly 4 times more energy than the same encounter between objects moving in the same direction. At 100 km/s, even a small rocky fragment carries the destructive power of a nuclear weapon. A direct hit from anything larger than a pebble would likely shatter Atlas's center completely. The thought experiment is both fascinating and terrifying. If Atlas were to encounter a significant space rock fragment, the collision would create a brief, brilliant flash visible from Earth-based telescopes. The center would break apart into a cloud of smaller fragments, each following its own hyperbolic trajectory out of the solar system. Within hours or days, what had been a single space visitor would become a scattered swarm of debris, impossible to track individually, and carrying away forever the secrets of its alien chemistry. Such an event would trigger immediate concerns about Earth's safety, despite the mathematical impossibility of any threat. Public imagination inevitably turns to worst-case scenarios when cosmic collisions make headlines. Could fragments be redirected toward Earth? Could a gravitational encounter with Jupiter or Mars send debris on an Earth-crossing path? The orbital mechanics provide clear answers. No. Atlas's hyperbolic trajectory carries far too much energy for gravitational deflection by any solar system object. Even a close encounter with Jupiter, by far our most massive planet, couldn't bend Atlas's path enough to threaten Earth. The fragments from any collision would continue on hyperbolic trajectories, racing out of the solar system and back into space between stars. More realistically, the true collision hazard for Atlas comes not from the named space rocks, but from the countless smaller objects that populate the belt. Fragments ranging from centimeters to meters in diameter are numerous enough to create a genuinely hazardous environment for any object with a large cross-sectional area. And as Atlas develops its cloud and tail, its effective size grows from a few kilometers to potentially hundreds of thousands of kilometers. The cloud represents a particular vulnerability. While the center itself is solid and relatively compact, the surrounding gas and dust cloud is thin and extended. Small particles striking the cloud won't destroy Atlas, but they could disrupt the delicate structures within the tail or trigger localized outbursts that change the comet's appearance dramatically. These micro-collision effects might actually be observable from Earth. Sudden brightness spikes, asymmetric jets, or changes in tail shape could all indicate interactions with belt material. Such events would provide unique insights into both Atlas's internal structure and the previously unmapped small particle population within the space rock belt. The gravitational effects of large space rocks present a different kind of hazard. While direct collision with Ceres or Vesta is essentially impossible, gravitational encounters could still influence Atlas's trajectory in subtle ways. These disturbances wouldn't redirect the comet toward Earth, but they might alter its spin rate, change the orientation of its rotation axis, or stress internal structures in ways that promote fragmentation. Perhaps most intriguingly, the space rock belt contains its own population of immigrants, objects that clearly formed elsewhere in the solar system before being scattered into their current orbits by planetary migration events. Some of these displaced objects might share compositional similarities with Atlas, having originated in the outer solar system where carbon dioxide ice is more common. An encounter with such an immigrant could provide fascinating comparative data about formation conditions throughout our stellar neighborhood. The Mars encounter on October 3rd deserves special attention in this context. At 0.19 astronomical units, Atlas will pass close enough for detailed observation by Mars-orbiting spacecraft, but far enough to avoid any gravitational complications. This represents an ideal compromise, scientifically valuable proximity without the risks associated with closer encounters. For the broader question of belt navigation, the survival statistics strongly favor Atlas completing its passage intact. The overwhelming likelihood is that it will thread through the most dangerous region of our solar system without encountering anything more substantial than microscopic dust. The belt may look crowded in artistic renderings, but the reality of celestial mechanics makes survival the overwhelmingly probable outcome. Yet the non-zero probability of collision adds dramatic tension to every observation. Each day that passes without incident increases confidence in Atlas's ultimate survival, while each unusual brightness variation or shape change raises questions about possible interactions with unseen belt material. The collision scenarios, however unlikely, remind us that space remains a fundamentally hazardous environment where high-energy encounters can erase billion-year journeys in milliseconds. Atlas has already survived forever of space travel, cosmic ray bombardment, and gravitational encounters with unknown objects in the galactic disk. The irony would be overwhelming if it were to be destroyed by debris from our own solar system's formation. But as each day passed without catastrophe, confidence grew that Atlas would emerge from the belt intact, carrying its cargo of alien chemistry toward the ultimate test of solar encounter. The collision scenarios remained possible, but survival was becoming probable, and survival meant answers to questions that had been traveling toward us since before our sun was born. Part 8. The Plasma Factor. As Atlas develops its growing cloud and tail, it's transforming from a simple rocky center into something far more complex and dynamic. A massive plasma laboratory conducting experiments that would be impossible to recreate on Earth. The physics at work here involves the fundamental interactions between matter, electromagnetic fields, and radiation that govern much of the behavior we observe throughout the universe. The process begins when solar ultraviolet radiation turns some of the neutral gas molecules, escaping from Atlas's center into ions. Carbon dioxide and water vapor, the primary components of its cloud, lose electrons and become positively charged ions floating in a sea of free electrons. This ionized gas, plasma, behaves very differently from ordinary matter, responding to magnetic and electric fields in ways that can seem almost alive. The solar wind, that invisible stream of charged particles, flowing outward from our sun at speeds of several hundred kms, doesn't simply flow around objects like a river around rocks. When it encounters the ionized cloud of a comet like Atlas, something remarkable happens. The plasma environments begin talking to each other through electromagnetic interactions. Fresh comet ions get picked up by the solar wind's magnetic field and accelerated to high speeds, creating what plasma physicists call mass loading. This process is somewhat like adding sandbags to a fast-moving river. The additional mass slows down the flow and changes its direction. For Atlas, the effect is even more pronounced because of its unusual chemistry. Carbon dioxide ions have different mass and charge properties than the water vapor ions that dominate most comet studies, potentially creating plasma behaviors that haven't been observed before. The European Space Agency's Rosetta mission provided detailed observations of mass loading effects at Comet 67 P. Churyumov-Gerasimenko documenting deflections of the solar wind by more than 45 degrees when the comet was active. The solar wind, which normally flows radially outward from the Sun, gets bent and twisted into complex patterns around the comet, creating magnetic field enhancements and wave structures that propagate both upstream and downstream. These electromagnetic interactions generate waves, magnetosonic waves, Alphen waves and other exotic oscillations that carry energy and information through the plasma environment. The waves can travel faster than the bulk motion of the plasma itself, providing a kind of early warning system that announces the comet's presence to the solar wind before the physical material arrives. For ATLAS, racing through the space rock belt on its backward trajectory, these plasma interactions take on additional complexity. The high relative velocities mean that encounters with the solar wind are more energetic than typical, potentially generating stronger wave signatures and more dramatic deflection effects. The near-ecliptic path ensures maximum interaction with the solar wind structures that are most common in the solar equatorial plane. The tail itself becomes a kind of cosmic windsock, its structure revealing information about solar wind conditions that can't be measured directly from Earth. When coronal mass ejections or high-speed stream interactions create disturbances in the solar wind, the plasma tail responds almost immediately. Magnetic reconnection events can literally disconnect sections of the tail, which then drift away while new plasma structures reform closer to the center. These tail disconnection events have been observed in numerous comets, creating some of the most dramatic time-lapse sequences in astronomical photography. The plasma tail appears to be yanked away by invisible forces, writhing and twisting as it interacts with changing magnetic field conditions. Within hours or days, a new tail reforms, only to potentially suffer the same fate when the next solar wind disturbance arrives. ATLAS's unusual carbon dioxide-dominated chemistry could make these interactions particularly spectacular. Carbon dioxide ions have different gyro-radii, the characteristic spiral patterns they follow in magnetic fields, compared to water vapor ions. This means the plasma tail might develop structures and instabilities that haven't been observed in previous comets, providing new insights into plasma physics under extreme conditions. The charging environment around ATLAS adds another layer of complexity. Dust particles in the cloud acquire electric charges through interactions with solar, ultraviolet radiation, plasma currents, and secondary electron emission. These charged grains then respond to both electric and magnetic forces in addition to gravity and radiation pressure, creating dust dynamics that can be chaotic and unpredictable. Laboratory experiments with dusty plasmas have revealed instabilities, wave phenomena, and collective behaviors that emerge when charged particles interact through long-range electromagnetic forces. In the environment around ATLAS, these effects operate on scales from micrometers to millions of kilometers, creating a natural laboratory for studying phenomena that bridge atomic physics and astrophysics. The solar wind conditions that ATLAS will encounter during its belt passage are particularly interesting from a space physics perspective. The ecliptic plane contains the most complex magnetic field structures, including sector boundaries where the solar magnetic field changes polarity, co-rotating interaction regions where fast solar wind catches up with slow wind, and the occasional passage of coronal mass ejections. Each of these structures will test different aspects of ATLAS's plasma environment. Sector boundary crossings can trigger sudden changes in tail shape. Co-rotating interaction regions can compress the cloud and enhance wave generation. Coronal mass ejections can completely reconfigure the magnetic field topology, potentially disconnecting the tail multiple times as the disturbance passes. Multiple spacecraft throughout the inner solar system are positioned to observe these interactions from different viewpoints. The Solar and Space Observatory, the Solar Dynamics Observatory, the Parker Solar Probe, and various Mars-orbiting missions can provide simultaneous measurements of solar wind conditions and ATLAS's response, creating three-dimensional maps of plasma interactions that would be impossible from Earth-based observations alone. The data from these plasma interactions will have implications far beyond comet science. Understanding how ionized gases behave under extreme conditions provides insights into star atmospheres, planetary magnetospheres, and the space medium itself. ATLAS is serving as a natural probe of plasma physics processes that operate throughout the universe. Perhaps most remarkably, the plasma environment around ATLAS is helping to create the very structures that make it visible from Earth. The ionized tail carries away not just individual atoms and molecules, but also the electromagnetic signatures of its alien chemistry. Every light line, every polarization measurement, every brightness variation carries information about materials formed around another star, now interacting with our local plasma environment. As ATLAS continues deeper into the space rock belt, these plasma interactions will intensify. The growing cloud will provide more material for ionization. The increasing solar radiation will drive stronger chemical processes. The complex magnetic field environment of the inner solar system will create more opportunities for dramatic tail interactions. The plasma factor wasn't just a scientific curiosity, it was becoming central to
ATLAS's survival prospects.
The electromagnetic forces at work in its cloud and tail could either help stabilize the center against fragmentation or contribute to internal stresses that promote breakup. The answer would depend on details of plasma physics that we were only beginning to understand. One thing was certain: ATLAS was no longer just a comet. It had become a plasma laboratory conducting experiments in fundamental physics while racing through the most dangerous region of our solar system. The results of those experiments would determine not just what we learned about space chemistry, but whether the ancient wanderer would survive long enough to reveal all its secrets. Part 9. Hidden Dangers, Dust and Tiny Crashes. While space watchers focus on the big possibility of ATLAS hitting a large space rock, the real dangers hiding in the belt are far more quiet and perhaps more dangerous. The space between Mars and Jupiter isn't empty. It's filled with countless bits ranging from tiny dust pieces to pebble-sized chunks, all moving at different speeds and creating a sand-blasting world that could slowly wear away the very secrets we're hoping to find. These tiny hits work on a completely different level than big crashes, but their total effect can be just as harmful over time. Every dust piece that hits ATLAS's center carries moving energy equal to the square of its speed. At typical belt-crossing speeds, even tiny particles hit with the force of small bullets, slowly wearing away surface material and possibly showing fresh layers beneath. The process is called space weathering, and it's been changing objects throughout our solar system for billions of years. On airless bodies like space rocks and moons, constant bombing by space dust slowly darkens surfaces, creates tiny glass balls, and changes chemical signs in ways that can hide the original makeup. For ATLAS, carrying precious samples of between-star chemistry, this wearing process could be destroying proof faster than we can study it. But wearing might also work in our favor. If ATLAS grew a radiation-darkened crust during its billions of years in between-star space, tiny hits could show fresher material beneath, showing chemical signs that would otherwise stay hidden. Some of the brightness changes and jets that telescopes are watching might result from exactly this process. Small hits, showing volatile, rich layers that then turn to gas quickly when heated by sunlight. The heat stress world adds another layer of difficulty. As ATLAS gets closer to the Sun, its surface temperature rises greatly, causing growth of the outer layers while the inside stays cold. These heat differences create mechanical stresses that can crack even solid rock, opening cracks that allow internal volatiles to escape. The result is often the explosive jets and bursts that make comet watching so hard to predict. Past examples suggest care. Comet C209Y4, also named ATLAS, began getting brighter greatly in early 2020, raising hopes for an amazing naked eye show. Instead, high-detail observations showed that the center was breaking apart, splitting into dozens of smaller pieces that slowly faded as they spread out. The breakup wasn't caused by any single big event, but rather by the built-up stresses of solar heating acting on an object that was already structurally weak. Comet Ison provides another warning tale. This promising sun grazer grew a beautiful tail and created enormous public excitement as it got closer to the Sun in 2013. But as it neared closest approach, tidal forces and intense solar heating beat its structural strength. Ison basically evaporated, leaving behind only a cloud of debris that quickly spread into space. The question for 3IATLAS is whether its unusual makeup makes it more or less likely to face these destructive processes. The carbon dioxide-rich chemistry found by the James Webb Space Telescope could mean either a tougher, more radiation-processed crust or a more volatile, fragile inside. Both situations have examples among solar system comets, but neither provides clear guidance for predicting the behavior of a between-star visitor. Age might be Atlas's enemy or its friend. If the object is indeed several billion years older than our solar system, it has survived cosmic ray bombing and heat cycling that would destroy less strong objects. This long survival might show unusual structural strength or makeup stability. On the other hand, the same processes that helped its survival might have left it brittle and likely to fail badly under the intense heating of solar approach. The watching signs of internal stress are becoming more clear as Atlas brightens. Sudden changes in brightness, uneven jets, and irregular changes in coma thickness all suggest that material is being released in bursts rather than smoothly. These outbursts could represent the opening of new vents as heat expansion cracks the surface, or they could show the beginning of structural failure. High-detail imaging campaigns are watching for the clear signs of breaking apart, multiple thick spots within the coma, stretching of the central brightness spread, or the appearance of separate centers following independent paths. The Hubble Space Telescope and ground-based adaptive optic systems can see features smaller than the center itself, providing early warning of any developing problems. The asteroid belt's dust world adds an outside stress to these internal processes. While individual dust hits are tiny, their collective effect over months of belt passage could be important. The growing coma around Atlas presents a large cross-sectional area for dust meetings, and high-speed impacts could cause localized heating that starts new outgassing events. Particularly interesting is the possibility that belt dust could interact with Atlas's unusual chemistry in unexpected ways. Most studies of dust impacts assume water ice-dominated makeups typical of solar system comets, but carbon dioxide behaves differently under impact heating, turning to gas at lower temperatures and possibly creating more explosive responses to external disturbances. The dust bands and zodiacal cloud that fill the inner solar system could create additional complications. These structures formed by dust spiraling inward from asteroid crashes create a background world of particle impacts that changes with location and time. As Atlas crosses different dust thickness regions, its brightness and tail shape might change in ways that reveal information about both the comet's properties and the previously unmapped dust world. One positive aspect of potential dust meetings is their scientific value. Even destructive impacts would expand our sample of between-star materials, spreading previously hidden interior makeup throughout the coma, where telescopes could study it with light analysis. In some sense, the asteroid belt dust might act as a natural drill, boring samples from Atlas's interior and making them available for remote study. The timing of these potential interactions is important. Each week that Atlas survives intact increases the scientific return from the mission, allowing more sophisticated measurements and longer-term watching of makeup changes. But each week also brings deeper going into the belt's most populated regions, increasing the chance of meetings with larger particles that could trigger more dramatic responses. Perhaps most importantly, the dust and tiny crash world represents a test that no other between-star visitor has faced. Neither Oumuamua nor Borisov developed significant comet activity while passing through dense particle worlds. Atlas is pioneering new territory, both literally and figuratively, as the first active between-star comet to navigate the asteroid belt's dangerous dust storms. The outcome would depend on factors we were only beginning to understand: the precise balance between Atlas's structural strength and the cumulative stresses of belt passage, the interaction between its unusual chemistry and the dust impact world, and the internal makeup gradients that determine how the object responds to external disturbances. Every observation was now critical, every brightness measurement potentially the last clear look at an intact between-star center. The hidden dangers of dust and tiny crashes weren't as dramatic as big asteroid impacts, but they might prove just as decisive in determining whether Atlas would survive to reveal its secrets or slowly break apart under the built-up stresses of navigating our cosmic neighborhood. The ancient wanderer was being tested in ways it had never experienced during its billion-year journey through between-star space, and the outcome remained far from certain. Part 10, Controlled or Self-Directed. In July 2025, as the world's attention focused on the newly found between-star visitor, a team of researchers published a thinking paper that would light imaginations and generate headlines around the globe. The research preprint, authored by Abraham Loeb and colleagues, presented what they called a teaching thought experiment: the possibility that 3IATLAS might not be a natural comet at all, but rather an artificially built object, potentially even hostile in purpose. The suggestion wasn't entirely new. Loeb had previously proposed that Oumuamua might represent alien technology, pointing to its unusual speed-up and lack of observable outgassing as potential proof of artificial construction. But Atlas presented a different puzzle. It was clearly active, developing the coma and tail expected of natural comets, yet its path and timing seemed almost suspiciously convenient for detailed study. The paper's language was carefully hedged with scientific caution, presenting the alien idea as one possibility among many rather than a definitive conclusion. But in the media world of 2025, nuanced academic thinking quickly transformed into sensational headlines. Tabloid coverage and opinion pieces escalated the language far beyond what the original researchers had proposed, creating a feedback loop of increasingly dramatic claims. The mainstream scientific response was swift and measured. NASA continued to classify Atlas as a natural comet, pointing to early light analysis observations that showed normal comet volatiles even in unusual ratios. The James Webb Space Telescope's detection of carbon dioxide and water vapor matched expectations for natural gas processes, even if the specific chemistry differed from typical solar system objects. More importantly, none of the watching signatures that would indicate artificial construction had been detected. Searches for radio signals at frequencies commonly used for communication found only natural heat radiation. The object's light curve showed variations consistent with an irregularly shaped spinning center, rather than the stable brightness expected from a constructed sphere or cylinder. No evidence of controlled speed-up beyond what could be explained by normal outgassing had been observed. The timing arguments that excited public thinking proved less compelling under closer analysis. While Atlas's near-ecliptic path did bring it through the most scientifically interesting regions of our solar system, orbital mechanics shows that any object entering from between star space has only limited possible paths. The apparent coincidence of optimal positioning might simply reflect the fact that we're most likely to detect and study objects that pass through regions where our telescopes can observe them effectively. The Mars encounter distance of 0.19 astronomical units, often cited as suspiciously convenient for observation, actually represents a fairly typical close approach for objects on hyperbolic paths. Random orbital mechanics produces such encounters regularly, and the fact that we have spacecraft at Mars to take advantage of the opportunity reflects human planning rather than alien intent. SETI researchers, while maintaining appropriate doubt about the alien idea, saw the thinking as an opportunity to conduct passive watching campaigns during key phases of Atlas's journey. Radio telescopes around the world scheduled opportunistic observations during the Mars flyby and solar approach, listening for any signals that might indicate artificial origin. The absence of detectable transmissions, while not ruling out technological construction, failed to provide supporting evidence for the idea. The search for mini-probes or deployed objects suggested in some media coverage found no observational support. High-detail imaging campaigns detected no separate objects traveling alongside Atlas, no evidence of material being deliberately released, and no structured patterns in the coma or tail that might indicate technological parts. Perhaps most significantly, the chemical signatures emerging from light analysis matched expectations for natural materials formed under alien stellar conditions. The carbon dioxide-rich makeup, while unusual for solar system comets, fit models for objects formed in the outer regions of planet-forming disks around different types of stars. The element ratios, when measurable, showed values consistent with natural star formation processes rather than the artificial element signatures that might result from technological construction. The thinking did serve to highlight important questions about how the scientific community should respond to genuinely unusual observations. The unusual properties of both Oumuamua and Atlas demonstrated that between-star visitors could exhibit behaviors outside the range of local experience, making it crucial to distinguish between naturally exotic phenomena and potentially artificial signatures. Media literacy became a critical factor in public understanding of the thinking. The progression from tentative academic idea to sensational headlines illustrated how scientific uncertainty can be amplified and distorted in public discussion. The original researchers' careful hedging and emphasis on teaching value was often lost in coverage that presented the alien idea as a serious scientific claim rather than a thought experiment. Cultural factors also played a role in the thinking's reception. The previous debates about Oumuamua had primed public audiences to view between-star visitors as potentially mysterious or artificial. Science fiction narratives about alien probes and first contact scenarios provided ready-made frameworks for interpreting unusual astronomical discoveries. The genuine scientific excitement about Atlas's unique properties could easily be reframed as evidence for more exotic explanations. The ethical implications of such thinking deserved consideration. If genuine evidence for artificial construction were ever detected, questions of disclosure, international coordination, and public communication would become critical. The Atlas thinking provided a useful rehearsal for how the scientific community might handle truly unusual discoveries in the future. But for the object racing through the asteroid belt in late 2025, the alien idea remained unsupported by observational evidence. The unusual chemistry that made Atlas scientifically fascinating was better explained by natural processes operating under foreign stellar conditions than by technological construction. The path that brought it through our most observable regions reflected the mathematics of orbital mechanics rather than intelligent navigation. The thinking had served its purpose as a thought experiment, generating public interest and highlighting the remarkable nature of between-star visitors. But as Atlas continued its journey towards solar encounter, the evidence pointed overwhelmingly toward a natural origin. An ancient comet formed around another star, carrying samples of alien chemistry that were precious precisely because they were natural products of cosmic evolution. The real mystery wasn't whether Atlas was artificial, but how natural processes in other stellar systems could produce objects so different from our local experience. That mystery was worth pursuing with the same intensity once directed towards thinking about alien construction, and the answers would prove just as fascinating as any science fiction scenario. As Atlas approached its closest solar encounter, the question wasn't whether it was controlled or self-directed. It was whether this natural marvel would survive long enough to reveal all the secrets of its alien chemistry and ancient history. Part 11, If Destroyed, a Broken Visitor. The scenario unfolds slowly, almost imperceptibly at first, as heat, stresses, and internal pressures build within Atlas's ancient center. What begins as subtle brightness changes and uneven jets evolves into something more dramatic. The slow motion, breaking apart of a between-star visitor that has survived billions of years only to give in to the intense environment of our inner solar system. The physics of comet breaking apart is both violent and strangely beautiful. As solar heating goes deeper into the center, volatile materials trapped within the ice rock matrix begin turning to gas rapidly, creating internal pressure that seeks release through the path of least resistance. Cracks that formed during eons of heat cycling in between star space become the focal points for explosive outgassing events that can literally blow the center apart. The visual progression would be unmistakable to experienced comet watchers. First, the central condensation, the bright core that represents reflected sunlight from the solid center, begins to stretch and develop multiple bright spots. High-detail imaging reveals that what was once a single object is becoming several, each following slightly different paths as they separate under the influence of spinning forces and uneven outgassing. Within days or weeks of initial breaking apart, the brightness behavior changes dramatically. Instead of the steady increase expected from normal solar heating, ATLAS exhibits rapid brightening followed by equally rapid fading as each fragment exhausts its surface volatiles and then becomes inactive. The overall coma expands and becomes more spread out, losing the sharp central condensation that characterizes an intact center. The tail structure responds immediately to breaking apart, developing multiple components as different fragments contribute their own gas and dust streams. What was once a coherent plasma tail becomes a complex braided structure reflecting the multiple ion sources now distributed along the comet's orbit. The dust tail, no longer fed by a single point source, spreads into a broad fan that can extend across significant portions of the sky. For Earth-based watchers, a breaking apart ATLAS would create both spectacular viewing opportunities and profound scientific disappointment. The increased surface area from multiple fragments often leads to enhanced brightness that can make comets visible to the naked eye, even at considerable distances. But the same breaking apart process that creates this temporary spectacle also destroys the pristine interior materials that represent our only samples of between-star chemistry. The meteor shower question inevitably arises whenever comet breaking apart occurs, but ATLAS's geometry provides reassuring answers. The fragments would continue following the same hyperbolic path as the original object, racing away from the Sun on paths that never intersect Earth's orbit. Unlike periodic comets that can deposit debris streams in Earth-crossing orbits, between-star visitors carry their fragments away from our neighborhood entirely. The dust and gas released by breaking apart could create more subtle effects. Enhanced zodiacal light, the faint glow caused by sunlight reflecting off space dust, might show temporary increases in regions where ATLAS debris concentrates. Radio observations might detect brief enhancements in plasma wave activity as the expanded ion cloud interacts more vigorously with the solar wind. But these effects would be localized and temporary, posing no threat to Earth or its technological systems. From a planetary dynamics perspective, ATLAS breaking apart would be essentially irrelevant. The total mass involved, probably less than a few trillion tons, represents a negligible perturbation compared to the gravitational influences that shape planetary orbits.
Even if every fragment somehow concentrated in one location, the gravitational effects would be too small to measure with our most sensitive instruments.
The scientific value of breaking apart presents a complex trade-off. On one hand, breakup destroys the structural integrity that preserves layered makeup and formation history within the center. The gradual mixing and dispersal of interior materials makes it impossible to determine their original distribution or the sequence of accumulation processes that built the comet during its formation around another star. On the other hand, breaking apart provides access to interior materials that would otherwise remain hidden beneath radiation-processed surface layers. Fresh fracture surfaces expose previously buried ices to light analysis, potentially revealing chemical signatures that were invisible when locked within the intact center. The expanding debris cloud creates a larger target for telescopic observation, making it easier to detect trace species and element ratios. The comparative studies with Comet ISON and C209Y4 provide frameworks for understanding how breaking apart progresses and what observational signatures to expect. Both objects showed similar patterns: initial brightening as surface area increased, followed by rapid fading as small fragments exhausted their volatile content. The debris clouds dispersed over periods of months to years, gradually becoming undetectable as they spread along extended orbital paths. High-detail imaging would be crucial for documenting the breaking apart process and determining whether it results from internal stress, external impacts, or some combination of factors. The Hubble Space Telescope's previous observations of breaking apart comets have provided detailed views of center breakup, revealing how individual pieces separate and evolve independently over time. The European Space Agency's Future Comet Interceptor mission, currently planned for launch in the late 2020s, was originally designed to study pristine comet centers from close range. If ATLAS were to break apart, the scattered debris might actually provide multiple targets for such missions, each representing different aspects of the original object's makeup and structure. Perhaps most poignantly, ATLAS breaking apart would represent the end of a story that began when our galaxy was younger and very different from its current state. An object that had wandered between the stars for billions of years, surviving cosmic ray bombing, gravitational encounters, and the harsh environment of between-star space, would give in not to some dramatic cosmic catastrophe, but to the gentle warming of our familiar sun. The emotional resonance of such an outcome shouldn't be underestimated. Comets have always represented impermanence in human consciousness, beautiful visitors that appear briefly before fading away forever. A between-star comet carries this symbolism to cosmic scales, embodying the vast time scales and distances that separate us from other stellar systems. Its destruction would be a reminder that even billion-year journeys can end in moments of geological time. Yet even in destruction, ATLAS would continue contributing to science. The dispersing fragments would carry element signatures and chemical traces into the outer solar system, where future missions might encounter and analyze them decades or centuries hence. The observational data from breaking apart would inform models of comet structure and makeup that would improve our understanding of similar objects for generations. The possibility of destruction was real, supported by historical precedent and the mounting evidence of internal stress revealed by ATLAS's erratic brightness behavior. But destruction wouldn't mean failure. It would simply represent a different kind of scientific revelation, one that traded long-term preservation for immediate access to materials that had been hidden since our galaxy's youth. As ATLAS continued racing toward its October solar encounter, the breaking apart scenario remained one possible outcome among many. The ancient wanderer might yet prove resilient enough to survive heat stress and emerge intact on the far side of closest approach. But if it didn't, if the stresses of solar encounter proved too much for billion-year-old ice and rock, then we would witness the spectacular end of a between-star journey that began when the universe itself was barely half its current age. Either way, ATLAS would teach us something profound about the nature of materials formed around other stars, the physics of objects that bridge stellar systems, and our own place in a galaxy filled with wandering worlds we're only beginning to discover. Part 12. If redirected, a new orbit. The fantasy has captured imagination since the first between-star visitor was detected. Could a chance gravitational encounter redirect ATLAS away from its hyperbolic path, trapping it permanently within our solar system? The scenario appeals to our deepest desires for cosmic companionship, the possibility that this ancient wanderer might abandon its billion-year journey to take up permanent residence among our familiar planets. The mathematics, however, tell a different story entirely. ATLAS carries a hyperbolic excess velocity of approximately 58 kilometers, representing kinetic energy far beyond what any solar system encounter could neutralize. To understand the scale involved, consider that even Jupiter, by far our most massive planet, can only alter an object's velocity by about 2 kilometers during a close flyby. Against Atlas's enormous hyperbolic energy, such perturbations are negligible corrections rather than fundamental redirections. Gravitational capture requires what orbital mechanics call a deep encounter, a close approach that allows a massive object to bend the incoming path through large angles while simultaneously bleeding off excess energy through tidal interaction or other dissipative processes. For Atlas, even the closest planetary approach occurs at Mars, where the flyby distance of 0.19 astronomical units represents a distant encounter by capture standards. The energy scales involved make permanent capture essentially impossible through gravitational means alone. Atlas would need to lose more than 99% of its kinetic energy to transition from a hyperbolic orbit to an elliptical one bound to the Sun. No combination of planetary encounters in our solar system could achieve such dramatic energy loss, particularly given the object's retrograde path that minimizes rather than maximizes gravitational assists. But subtle redirections are indeed possible and potentially observable. Mars could alter Atlas's path by small amounts, changing the precise timing of solar approach or slightly modifying the departure angle. Venus, at 0.65 astronomical units in November, might provide additional minor perturbations. The cumulative effect of these encounters could shift Atlas's ultimate exit path by measurable amounts without fundamentally changing its hyperbolic nature. More intriguingly, non-gravitational forces could play a role in path modification. The uneven outgassing that creates comet tails also generates small but persistent accelerations that can accumulate over time. If Atlas develops strong directionally biased jets during its solar approach, these forces could act like tiny rocket engines, nudging the path in ways that complement gravitational perturbations. The Rosetta mission documented how outgassing forces can significantly alter comet orbits over multiple closest approach passages. For the 67P Churyumov-Gerasimenko, uneven jets change the orbital period by several minutes per orbit, small effects that accumulate into major changes over thousands of years. Atlas, with its unusual carbon dioxide-rich chemistry, might experience outgassing patterns different from typical water-dominated comets. However, even dramatic non-gravitational accelerations couldn't overcome Atlas's fundamental hyperbolic nature. The object carries too much energy for capture, regardless of how its path might be modified by outgassing effects. Any redirection would simply change which direction it exits our solar system rather than preventing departure entirely. The concept of hiding in the belt presents another intriguing but ultimately impossible scenario. Some thinking scenarios have suggested that Atlas might somehow become trapped among the asteroid belt objects, disguising itself as a local resident while secretly maintaining its between-star origin. The orbital mechanics make this fantasy impossible. Hyperbolic paths don't permit closed orbits around the Sun, regardless of where they might pass through the solar system. Post-closest approach observations will be crucial for documenting any path modifications that do occur. Atlas is scheduled to reappear from solar conjunction in early December 2025, providing opportunities to measure any changes in its orbit resulting from solar encounter and planetary perturbations. These measurements will help refine models of non-gravitational forces and improve predictions for future between-star visitors. The observational opportunities extend well beyond simple path tracking. Multiple spacecraft throughout the inner solar system might catch glimpses of Atlas during different phases of its journey, providing parallax measurements that improve orbital determinations and reveal subtle perturbations. The Mars encounter on October 3rd represents a particularly valuable opportunity for spacecraft in orbit around the Red Planet. NASA's Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Mars Express, along with surface-based assets like the Perseverance rover, all carry instruments capable of detecting bright comets under favorable circumstances. While the logistics of coordinating such observations are complex, the potential scientific return could justify the effort required to schedule special observations. The path modifications, however small, carry implications for broader questions about between-star object populations and their interactions with planetary systems. Understanding how solar system encounters alter the paths of visiting objects helps astronomers model the long-term evolution of between-star populations and predict detection rates for future surveys. Perhaps most importantly, careful path monitoring provides tests of our understanding of non-gravitational forces and plasma interactions. If Atlas's departure path differs from gravitational predictions by measurable amounts, those differences can be attributed to outgassing forces, radiation pressure effects, or electromagnetic interactions with the solar wind. Each measurement refines our knowledge of how between-star materials respond to stellar environments. The ultimate fate remains clear. Atlas will depart our solar system on a modified but still hyperbolic path, carrying its samples of alien chemistry back into between-star space. The precise direction of departure and the exact timing of solar system exit might be altered by solar encounter, but the fundamental outcome, a return to the galactic wilderness, cannot be changed by any realistic combination of gravitational and non-gravitational forces. This certainty brings both disappointment and relief. The disappointment comes from our inability to retain this remarkable visitor for extended study. The relief comes from the knowledge that Atlas will continue its cosmic journey, potentially carrying samples of our solar system's environment to other stellar neighborhoods billions of years in the future. In a sense, Atlas represents a cosmic ambassador, sampling conditions around different stars and spreading materials between stellar systems on timescales comparable to galactic evolution. Its brief visit to our neighborhood is just one episode in a story that spans galactic history, connecting stellar systems across space and time in ways that dwarf human comprehension. The redirection scenarios, however appealing to our imagination, cannot overcome the fundamental physics of between-star paths. Atlas will remain a visitor, not a permanent resident, departing our solar system with slightly modified momentum but undiminished mystery. The brief encounter will leave us with data, memories, and questions that will outlast our own civilization's ability to remember this ancient wanderer from the stars. Part 13, the alien idea expanded. The thinking that began with a single research preprint in July 2025 had evolved into something far more complex and contentious by the time Atlas reached its asteroid belt crossing. What started as an academic thought experiment, could this between-star visitor represent alien technology, had morphed through media amplification and public imagination into claims that seemed to take on lives of their own. Abraham Loeb and his colleagues had carefully framed their original paper as teaching, using phrases like possibly hostile, not as definitive claims, but as extreme examples designed to illustrate how extraordinary evidence would be required to support extraordinary ideas. The scientific method demands that all possibilities be considered, even unlikely ones, provided they generate testable predictions that can distinguish between competing explanations. But the progression from scientific thinking to public narrative illustrated how extraordinary claims can outpace the evidence that supports them. Social media algorithms designed to promote engagement, rather than accuracy, amplified the most sensational interpretations, while often omitting the careful hedging and uncertainty measurement that characterized the original research. The scientific community's response remained measured and evidence-based. NASA's official position classified Atlas as a natural comet based on multiple lines of observational evidence. The light analysis signatures detected by the James Webb Space Telescope and ground-based observatories matched expectations for natural gas processes, even if the specific chemistry differed from typical solar system objects. More critically, none of the smoking gun signatures that would indicate artificial construction had been detected despite intensive monitoring by multiple facilities. Radio surveys found no coherent transmissions at frequencies commonly used for communication or navigation. Optical monitoring revealed no evidence of controlled acceleration beyond what could be explained by normal outgassing processes. High-detail imaging showed no geometric structures or surface features incompatible with natural formation. The burden of proof for extraordinary claims requires extraordinary evidence, and such evidence simply hadn't materialized despite months of detailed observations. The alien idea remained possible in the abstract sense that most unfalsifiable propositions remain possible, but it lacked the observational support that would elevate it from thinking to serious scientific consideration. SETI researchers, while maintaining appropriate scientific doubt, had embraced the opportunity to conduct passive monitoring campaigns during key phases of Atlas's journey. The Breakthrough Listen project and other radio survey initiatives scheduled dedicated observation time around critical dates: the Mars encounter, solar approach, and departure phases, when any hypothetical technology might be most likely to activate or communicate. The absence of detectable signals, while not definitively ruling out technological origin, failed to provide the positive evidence that would be required to support such claims. In science, negative results carry weight. They constrain the parameter space of possible explanations and eliminate ideas that make specific testable predictions. The search for deployed objects or mini-probes had similarly yielded negative results. Multiple high-detail imaging campaigns, including observations by the Hubble Space Telescope and ground-based adaptive optic systems, detected no separate objects traveling alongside Atlas, no evidence of structured material release, and no geometric patterns in the coma or tail that might indicate technological components. Perhaps most significantly, the element signatures emerging from detailed light analysis matched expectations for natural materials formed through stellar formation processes. The carbon, oxygen, and hydrogen element ratios, when measurable, fell within ranges predicted for objects formed in different galactic environments, rather than showing the artificial signatures that might result from technological construction or propulsion systems. The cultural context surrounding these thoughts deserved analysis in its own right. The previous debates about Oumuamua had established between star visitors as potentially mysterious objects worthy of exotic explanations. Science fiction narratives about alien probes, first contact scenarios, and hidden technological surveillance provided ready-made interpretive frameworks that could be applied to any unusual astronomical discovery. Media coverage often emphasized the most sensational possibilities while downplaying the careful uncertainty measurement that characterizes responsible scientific communication. Headlines that proclaimed, "Scientists say comet could be alien probe," rarely conveyed the conditional language, probability assessments, and alternative explanations that appeared in the original research papers. The phenomenon highlighted important questions about science communication in an era of rapid information dissemination and algorithmic amplification. How should researchers balance legitimate scientific thinking with public understanding? What responsibilities do scientists have when their ideas are misrepresented or sensationalized in popular media? Educational opportunities emerged from the controversy. The alien thinking provided teachable moments about the scientific method, the nature of evidence, and the process by which extraordinary claims are evaluated within the scientific community. The progression from idea to testing to conclusion offered clear examples of how science distinguishes between thinking and established knowledge. The ethical implications of such thinking also warranted consideration. If genuine evidence for artificial construction were ever detected, questions of disclosure, international coordination, and public communication would become critical. The Atlas controversy provided a useful case study for how the scientific community might handle truly unusual discoveries in future encounters. But perhaps most importantly, the alien thinking had served to highlight just how remarkable Atlas was as a natural object. The unusual chemistry, the convenient path, the timing of discovery, all the factors that made technological origin seem plausible were actually evidence for the incredible diversity of natural processes operating throughout our galaxy. The carbon dioxide-rich makeup revealed formation conditions unlike anything in our local stellar neighborhood. The near-ecliptic path demonstrated that between star space contains objects following every conceivable orbital geometry. The detection timing reflected our improving ability to discover and characterize objects that would have remained invisible to previous generations of telescopes. In a very real sense, ATLAS was far more interesting as a natural phenomenon than it would have been as alien technology. Technological objects, however advanced, operate within constraints imposed by physics, engineering, and presumed rational purposes. Natural objects, shaped by processes we don't fully understand, operating under conditions we can barely imagine, can exhibit behaviors that transcend our current theoretical frameworks. The real mystery wasn't whether ATLAS was controlled by alien intelligence, but how natural processes in foreign stellar environments could produce objects so different from our local experience. That mystery was worth pursuing with the same intensity once directed towards thinking about technological construction, and the answers would prove just as profound as any first contact scenario. As ATLAS continued its journey through the asteroid belt, the evidence pointed overwhelmingly toward a natural origin, not because aliens were impossible, but because the natural universe was strange enough to explain everything we were observing. The cosmos didn't need artificial enhancement to generate objects that challenged our understanding and fired our imagination. The alien idea had done its job, encouraging rigorous observation and analysis while generating public interest in between-star visitors. But the natural explanation emerging from that analysis was proving far more fascinating than any science fiction alternative. ATLAS was teaching us that reality, when viewed on cosmic scales, could be more exotic than our wildest thoughts about alien technology. Part 14, the wake-up call. The detection of ATLAS represented more than just another astronomical discovery. It was a preview of our future, a glimpse into an era when between-star visitors might become routine rather than extraordinary. Our current sky surveys, impressive as they seem to contemporary watchers, capture only a tiny fraction of the objects passing through our cosmic neighborhood at any given time. The catalogs maintained by NASA, ESA, and ground-based survey programs contain millions of known objects, from near-Earth asteroids to distant Kuiper Belt residents. But these databases, comprehensive as they appear, represent primarily objects that belong to our solar system, permanent residents bound by the sun's gravity and following predictable orbits that can be calculated centuries into the future. Between-star visitors present entirely different challenges. They appear without warning from random directions, follow hyperbolic paths that carry them quickly through our detection zones, and often remain visible for only weeks or months before fading beyond instrumental limits. The discovery of ATLAS, like its predecessors Oumuamua and Borisov, depended as much on luck and timing as on systematic search strategies. This situation is about to change dramatically with the completion of the Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope. Beginning operations in the mid-2020s, this revolutionary facility will conduct a decade-long survey of the southern sky, imaging the entire visible universe every few nights with unprecedented depth and precision. Current estimates for between-star object detection rates vary widely depending on assumptions about size distributions, approach geometries, and instrumental sensitivity limits. Conservative projections suggest the Rubin Observatory might detect 1 to 2 between-star visitors per year, a tenfold increase over current discovery rates. More optimistic scenarios based on theoretical models of galactic object populations predict dozens of detections annually once the survey reaches full operational capability. The implications of such discovery rates extend far beyond simple object catalogues. Each between-star visitor carries unique chemical signatures and formation histories from different stellar environments. Systematic studies of multiple objects would reveal patterns and correlations impossible to detect from individual cases like ATLAS. Statistical analysis of between-star populations could constrain models of planetary formation, stellar evolution, and galactic chemical evolution. But increased discovery rates also create new challenges for rapid response observation and characterization. ATLAS benefited from months of advanced warning and coordinated observational campaigns involving multiple facilities worldwide. If between-star visitors become numerous enough, the astronomical community will need automated detection algorithms, pre-planned response protocols, and flexible scheduling systems that can adapt to unexpected discoveries. The ATLAS experience has provided valuable lessons for managing future between-star encounters. The coordination between NASA, ESA, NOILAB, and international partners demonstrated how effectively the global astronomical community can mobilize resources when presented with rare opportunities. The rapid deployment of space-based assets like the James Webb Space Telescope and Hubble showed the value of flexible scheduling and priority override capabilities. Perhaps most importantly, ATLAS has served as a dress rehearsal for public communication and media management during high-profile astronomical events. The progression from technical discovery, announcements to widespread public interest to sensationalized thinking illustrated both the opportunities and challenges associated with communicating cutting-edge science to general audiences. The planetary defense angle adds another layer of complexity to between-star object detection and characterization. While ATLAS posed no threat to Earth, future visitors might follow paths that bring them closer to our planet or its orbital path. Distinguishing between harmless between-star visitors and potentially hazardous objects requires rapid orbit determination and accurate size estimation capabilities that current survey systems are still developing. The technical infrastructure for handling increased detection rates is gradually taking shape. Machine learning algorithms can now identify moving objects in survey data with accuracy approaching that of human analysts. Automated follow-up systems can trigger light analysis observations at multiple facilities based on predefined criteria. Communication networks can disseminate discovery information to the global astronomical community within hours of detection. Educational opportunities multiply as between-star visitors become more common. Each new discovery provides fresh examples for discussing stellar formation, planetary dynamics, and the chemical evolution of galaxies. The diversity of objects, some resembling familiar solar system bodies, others exhibiting completely alien properties, offers natural laboratories for comparative planetology on between-star scales. The data archival and analysis challenges are equally significant. Each well-observed between-star visitor generates terabytes of imaging, light analysis, and brightness data that must be processed, archived, and made available for future research. The ATLAS dataset, accumulated over months of intensive observations, will serve as a reference standard for comparing future discoveries and testing theoretical models. International cooperation becomes even more critical as detection rates increase. No single nation or observatory system can comprehensively characterize multiple simultaneous between-star visitors. Sharing telescope time, coordinating observations, and pooling analytical expertise require agreements and protocols that transcend traditional institutional boundaries. The technological implications extend beyond astronomy into spacecraft design and mission planning. If between-star visitors prove common enough, dedicated interceptor missions become feasible, spacecraft stationed at strategic locations within the solar system, ready for rapid deployment to rendezvous with newly discovered objects. Conceptual studies for such missions already exist in the literature, awaiting sufficient detection rates to justify their development. Amateur astronomers will play increasingly important roles in between-star visitor detection and monitoring. Modern CCD cameras and computerized telescopes have democratized astronomical observation to an extent unimaginable just decades ago. Distributed networks of amateur watchers can provide continuous monitoring that professional facilities, with their competing priorities and limited telescope time, cannot match. The wake-up call represented by ATLAS extends beyond technical preparedness to philosophical readiness. As between-star visitors become routine, human perspective on our place in the galaxy will inevitably shift. We are not isolated residents of a unique stellar system, but participants in a vast galactic ecosystem where materials, and possibly life itself, migrate between stars on timescales measured in millions and billions of years. Each between-star visitor represents a cosmic messenger carrying samples of chemistry and physics from stellar environments we may never visit directly. The accumulated data from dozens or hundreds of such objects will provide insights into galactic evolution, planetary formation processes, and the distribution of organic materials throughout our local region of the
Milky Way. The preparedness isn't just about defense or scientific opportunity.
It's about recognizing our membership in a much larger cosmic community. The materials in our own bodies, forged in stellar cores and dispersed by supernovae, share common origins with the substances traveling between stars aboard objects like Atlas. We are studying not alien chemistry but distant relatives in the vast family of cosmic materials. As Atlas continues its passage towards solar encounter, it carries with it the hopes and preparations of an astronomical community learning to expect the unexpected. The ancient wanderer has already taught us that our cosmic neighborhood is far more dynamic and interconnected than previous generations ever imagined. The visitors yet to come will complete that education, transforming between-star objects from rare curiosities into familiar representatives of our galactic heritage. The wake-up call has sounded. The era of routine between-star visitor encounters is beginning, and Atlas has shown us both the opportunities and challenges that await in our expanding cosmic awareness. Part 15, Conclusion, the Cosmic Mirror. As Atlas races through the final phases of its asteroid belt crossing, preparing for its October encounter with our Sun, it carries with it more than just ancient ice and alien chemistry. This wanderer from the galactic depths has become a mirror in which we see reflected our own place in a universe far stranger and more interconnected than previous generations could have imagined. Whether Atlas survives its solar encounter intact, gradually breaks apart under heat stress, or fragments spectacularly across our skies, it has already fulfilled its most important function as cosmic messenger. Every spectrum, every brightness measurement, every shape detail captured by our telescopes adds to a growing understanding of how materials circulate between stellar systems, carrying with them the chemical signatures of distant worlds. The retrograde path that threads Atlas directly through our solar system's most populated regions serves as a reminder that cosmic traffic flows in all directions, following paths determined by gravitational dynamics that operate on galactic scales. The same orbital mechanics that govern planetary motion around our Sun shape the wandering paths of objects scattered between the stars, creating encounters like this one that bridge stellar neighborhoods separated by light years of space. Atlas's unusual chemistry, that carbon dioxide-rich signature detected by the James Webb Space Telescope, provides a tantalizing glimpse into formation conditions around stars very different from our own. The ratios of volatiles, the element signatures, the physical properties all speak to planet-forming environments where temperature gradients, radiation fields, and chemical abundances created objects unlike anything in our local experience. There is profound beauty in this ordinariness made extraordinary by distance and time. Atlas isn't miraculous or supernatural. It's a natural product of stellar formation processes operating under slightly different conditions than those that shaped our own solar system. Yet those subtle differences, magnified by billions of years of evolution, have created an object that challenges our understanding of planetary formation and chemical evolution throughout the galaxy. The philosophical implications extend beyond scientific discovery into questions of cosmic perspective and human significance. We are watchers of processes that began when our galaxy was younger and very different from its current state. The materials now turning to gas from Atlas's center were incorporated into solid form when entire generations of stars were being born and dying in stellar nurseries we can barely detect with our most powerful telescopes. Each photon of reflected sunlight, each spectral line revealing molecular makeup, connects us directly to conditions that existed billions of years before our own planet formed. We are literally looking backward in time, not through telescopic observation of distant light sources, but through direct analysis of materials that have preserved the chemical signatures of ancient galactic environments. The technical achievements represented by ATLAS observations demonstrate how far human capability has advanced in understanding our cosmic environment. The coordination between space-based telescopes, ground-based observatories, and theoretical models has created an analytical framework that can extract detailed information from objects moving at hypervelocity through our solar system. We have become cosmic archaeologists, reading formation histories from materials that predate our existence by billions of years. Yet the encounter also highlights the vast scales of ignorance that still surround us.
ATLAS represents just one sample from the Milky
Way's thick disk population, one data point in a distribution that contains billions of similar objects following their own wandering paths through between-star space. The diversity of chemistry, makeup, and formation history represented by the full population remains almost entirely unknown. The practical implications for future discoveries are equally profound. ATLAS has served as a preview of the era that awaits when the Vera C. Rubin Observatory begins detecting between-star visitors routinely rather than accidentally. The techniques developed for rapid characterization, the international coordination protocols, the public communication strategies, all address rehearsals for managing a future where between-star visitors become familiar rather than extraordinary. The safety questions that inevitably accompany any discussion of incoming cosmic objects have been definitively answered for ATLAS. The closest Earth approach of 1.8 astronomical units places it well beyond any possibility of direct interaction with our planet. Even complete breaking apart would produce debris following the same hyperbolic path, carrying all fragments away from Earth rather than toward it. This safety provides the luxury of pure scientific appreciation, free from the anxiety that accompanies potentially hazardous objects. ATLAS can be studied for what it teaches us about galactic evolution, planetary formation, and between-star chemistry without the overlay of threat assessment that characterizes near-Earth object research. The cultural impact of ATLAS extends beyond scientific literature into broader human consciousness of our place in cosmic time and space. The realization that our solar system receives regular visits from objects formed around other stars fundamentally changes perspective on isolation and connectivity. We are not alone in the sense that fictional narratives often imagine, but we are connected through material processes that operate on scales both intimate and vast. The dust that ATLAS sheds as it approaches our Sun will join the zodiacal cloud that fills space between planets, mixing between star materials with the debris from solar system formation. Future spacecraft and perhaps future human explorers will encounter these particles without knowing their extraordinary origin. Between-star chemistry will become part of our local environment, indistinguishable from materials that never left our stellar neighborhood. In this sense, ATLAS represents both arrival and departure, visitation and integration. The object itself will race away from our Sun on a modified but still hyperbolic path, carrying samples of our solar wind environment back into the galactic wilderness. But the materials it leaves behind, the gases and dust that form its coma and tail, will remain with us, permanent additions to our local cosmic environment. The observational campaign continues as ATLAS approaches solar encounter, but the most important discoveries have already been made. We have confirmed that between-star space contains a diverse population of objects carrying chemistry from throughout our galaxy's history. We have demonstrated that natural processes in foreign stellar environments can produce materials with properties that challenge our theoretical understanding. Most importantly, we have shown that our solar system is not an isolated island but a way station in a vast network of material exchange that connects all stellar systems across cosmic time. As ATLAS fades from our telescopes, whether through survival and departure or through breaking apart and dispersal, it leaves behind a transformed understanding of our place in the galactic community. We are citizens of a universe far more dynamic and interconnected than we previously imagined, participants in processes that link stellar formation throughout our region of the Milky Way. The ancient wanderer has delivered its message, written in the universal language of physics and chemistry. The translation continues, but the essential meaning is already clear. We are not alone. We have never been alone. And the materials that make up our world participate in exchanges that span the galaxy and bridge eons of cosmic time. The cosmic mirror reflects not isolation, but connection, not uniqueness, but participation in processes that extend from our local neighborhood to the most distant stars visible in our night sky. Atlas has shown us our reflection in that mirror, and the face looking back is both familiar and wondrously strange, ancient and eternal, local and cosmic. The next visitor is already on its way, carrying fresh messages from stellar systems we will never see directly. The conversation continues, written in the eternal language of wandering worlds.